impulse function. So this is another type of functions that you're going to encounter in reality. You see a lot of this in real world situations, such as in mechanics, in electrical engineering, in sound engineering. So we talk about the impulse function, how to set it up, and it can act, the impulse functions can act as a right-hand side of the initial value problem of the differential equations, or in a way it's the forcing terms that you see on the right-hand side of differential equations. So the learning objective of this lecture is to define what is the impulse function, and another thing is what is the Dirac delta functions, and hopefully you could be able to distinguish the two types of functions. They are similar, but the Dirac delta function is kind of the a specific case of the impulse functions. And then, of course, at the end of the day, the focus is to find the Laplace transform and the inverse Laplace transform of the impulse functions. Okay. So what is an impulse, right? In physical terms, an impulse represents an input that delivers a fixed amount of something like force or charge in a very short amount of time. That's the definitions of impulse, right? But where do you see this type of physical interpretations of impulse, right? So it occurs a lot in many places. Impulse in mechanics, right? When you strike a hammer on something, right? On metal, on wood, right? It creates a deafening sound if you are close enough. That's an impulse, right? When you fire a gun, that's an impulse. The sound that you hear, that's an impulse. Right? When you kick a soccer ball, right? You hear a boom. That's an impulse, right? When you watch a baseball game and a hitter hit a baseball, that sound that created by the connection between the bat and the baseball, that's create an impulse. That's a sound that you hear. When you have a lightning strike on a power line, right? You hear very loud noise, deafening noise. That's an impulse. Right? Or a very short voltage spike, a click on in a digital audio editing to test system respond, so that's an impulse as well. When I record videos like this and the audio or the machine pick up a lot of noises, not only my voice but the surrounding noise that I have, like an AC is running right now, I kick my leg here a little bit, when I write I have a tapping noise here, as you can hear. So those are the impulses that occur in everyday life situations, and because it's occurred a lot in a lot of places, many times, so that's why it's important to learn this type of functions and how to deal with that in terms of finding Laplace transform and inverse Laplace transform. Okay, so in general, mathematically, what does that mean? Like, what type of function is that? So I'm going to introduce to you two type of functions, two type of impulse functions. Like, one is kind of a general impulse function, and one is more of a specific case scenario. So for in unit impulse functions, so the functions of the form written in this form, that is delta sub a of t minus t0. So this is a function in terms of t. The t minus t0 is that you slide it or you translate it or you shift it to the right by a t sub 0 units. Okay, so the value of a will indicate that's kind of the interval that you are dealing with. You will see the setup in a minute, and that is the impulse functions. Okay, so let me write down the setup for the delta function here. So delta sub a of t minus t0 is equal to the piecewise defined function of, this is going to be 0 when t is between 0 and t0 minus a, and equal to 1 over 2a when t is between t0 minus a and t0 plus a. And it's going to be 0 again when t is greater than or equal to t0 plus a. Right. So that's the setup. Right. The function is 0 everywhere except in the interval between t0 minus a and t0 plus a, as you can see in this graph. Okay. So the function is 0 on the left of t0 minus a, or in the interval between 0 and t0 minus a. It's going to be 0 again when t is greater than or equal to t0 plus a. But the function is equal to 1 over 2a. You have a constant function when t is between t0 minus a and t0 plus a. Right, so in a way, you can shorten this function a little bit. That is, the function is equal to 1 over 2a when t is between t0 minus a and t0 plus a, and is 0 otherwise. So this is called a unit impulse because it's possessed the integration property. So this is a very important assumption. That is the improper integral of the delta function of the unit impulse functions. It's going to be equal to 1. From 0 to positive infinity of delta sub a of t minus t0 dt is equal to 1. Right, when you take the integral of this function and the calculations add up to 1 or equal to 1, you can think of this particular integral or this particular evaluation as a property, right? As a probability. Okay. When you study statistic and probability, the probability of an event is going to be, or the sum of all the probabilities add up to 1. Right? The applications of definite integral from one point to another point is equal to 1. Right? So that's the kind of the explanations for where this is coming from. Okay. So now go back to this graph. So the graph for this is the graph of a delta functions. Right? Why is the reason of 1 over 2a? This is convenient for us so that when you find the area under the curve, even though there's no curve here, it's just the horizontal line. So the area of this rectangle right here, when you find the area of this rectangle is going to be t0 plus a minus t0 minus a for the width, multiplied with the height, which is 1 over 2a. So 1 over 2a times 2a is equal to 1. Because of the property that you need to impose on this type of function, that's why the functions that you choose has to be 1 over 2a. Okay, so hopefully I addressed that. When a is small enough, you have a very large functions, large amount of something. So 1 over something very small give you something very large. So for a small value of a, delta sub a of t minus t0 is essentially a constant function with a large magnitude that is on for a very short period of time. Right, so that's the setup for the impulse functions. Now, more specifically, you have a direct delta functions. In practice, it is convenient to work with another type of unit impulse functions called direct delta functions. So we will work with another function that approximates the unit impulse function here, and it's defined by the limit. So this is very similar to what you see earlier, but the notation is just delta of t minus t0. Right? That is the limits of this impulse function as a going to be at h approaches 0, it's going to be just delta of t minus t0. So this function is called the direct delta function, and the function can be characterized by two properties. The first one is that the delta function or the direct delta function is also a piecewise defined function and is equal to 0 when t is different from t0. Because remember, at this point, you take the limit of the delta sub a functions as a equal to 0, so that's why you only see t0 left in the function and no a in the function whatsoever. And then it's going to be equal to positive infinity. The sound that you hear, the deafening sound that you hear, kind of like will shoot up to 0, and everything kind of concentrated at the location of t equal to t0. And of course, characterized by the distributions here, or it's called the improper integral from 0 to positive infinity of delta of t minus t0 dt equal to 1. Okay. Again, this is called the direct delta functions, and this is the graph, right? So you have, let's say this is from t0 minus a, this is t0 plus a. and it gets smaller and smaller as a approaches 0. So you concentrate it at one location here, at t0, and the cell gets shoot up, or the function gets shoot up to positive infinity at t equal to t0. In the case of t0 concentrated at 0, we get that. So I'm gonna give you something very similar to this, but for the case of t0 is equal to 0, not something in time, not something that is greater than 0. So when t0 equal to 0, we get that delta of t is equal to limit of delta sub a of t as a equal to 0. Okay. Here, the function is characterized by the two properties. The first one is how you define the delta functions, how you define the Dirac delta functions. So very similar to the general definitions here, that is the delta function or Dirac delta function is equal to 0 when t is different from 0 and is equal to positive infinity when t is equal to 0. Again, very similar to what you see here. It's just that I'm considered t0 at 0. Okay, so that's why the formula is slightly changed a little bit. Okay, and the distributions or the improper integral from 0 to positive infinity of delta t dt is going to be equal to 1. So that's the two properties that I want you to see. And to annotate this information a little bit, so this graph kind of showing the behavior of delta sub a of t minus t0 as a approaches 0. Okay. So that's the unit impulse function in Dirac delta functions. So Dirac delta function is a limit of the unit impulse functions, right? And the limit as a approaches 0. The concept is very similar, of the two functions are very similar. That is, even for Dirac delta function, it depends on the function 1 over 2a. Here is that we take the limit as a equal to 0, that's why it gets shot up to positive infinity. And the distribution is the same for both cases, right? So the distribution or the improper integral has to add up to 1. Here I also present to you a very specific case of t0 at 0. Now, moving on to something called the shifting properties. Integrating a function against delta function or Dirac delta function has an effect on shifting or testing for value of the function as the origins. So you have this function that the improper integral from negative infinity to positive infinity. So this is kind of a general formula of f of t times delta of t dt is equal to f of 0. Okay, I would like to show you where it's coming from a little bit later. And in the general situations, we want to generalize this information right here. So to generalize this property, the delta function has the property that the improper integral from negative infinity to positive infinity of f of t multiplied with delta of t minus t0 dt is equal to f of t0. Okay. So you have a functions, right? So f of t or x of t in this case is a function, the function in blue, and you have a Dirac delta function in dashed orange. What is the for this shifting function is that is concentrate at a certain location, pick out that information, and the product of this, when you do the calculations and evaluate the integral from negative infinity to positive infinity, it's going to give you something like this. Okay, so this gives you that information. And you're going to see this type of calculations again in the next lecture. This is just, I want to set this up, I want to give this a property because this property pop up again in another concept in mathematics in differential equations. It's called convolutions, right? Okay, so I want to show you how this is even possible. How can we get this going from here, and for some reason you get f of 0. So to show that the improper integral from negative infinity to positive infinity of f of t delta t dt equal to f of 0, we consider the expressions f of t times delta of t. That is, we can replace f of t times delta of t by something. Okay. Since the impulse is 0 everywhere except at t equal to 0, we can replace f of t times delta of t by f of 0 times delta t, or what we have for the improper integral is from negative infinity to positive infinity of f of t delta t dt equal to the improper integral from negative infinity to positive infinity of f of 0 times delta of t dt. And now at this point, because f of 0 is a constant, it's just the evaluation of the function at t equal to 0, you can pull f of 0 out of the integral operations. So f of 0 times the improper integral from negative infinity to positive infinity of delta t dt. So with this improper integral, you don't have to do any calculation. It's just the assumption that one of the properties of direct delta function is that the distribution from 0 to positive infinity is going to be equal to 1. Now you can definitely extend this to the left-hand side as well and include from negative infinity to positive infinity, because delta t is 0 everywhere, so you can extend to the left-hand side as well. And therefore, this particular distribution right here is equal to 1. And because of this, you have is equal to f of 0. So from the improper integral right here, you get f of 0. Okay. So this explanation right here, since the impulse is 0 everywhere except at t equal to 0, we can replace f of t times delta of t by f of 0 times delta of 0. This is a very vague explanation. So I want to dive a little bit deeper into this explanation. I just want to give you this explanation and give you the answer first to see where actually is coming from. But now I want to go back and explain this concept a little bit further. Okay, so how could we get this? We go back to the idea of just the unit impulse function, not just the direct delta function, just the unit impulse functions. That is, so consider, so I'm going to use a different color here, so consider the functions of the form from negative infinity to positive infinity of f of t times delta sub a of t dt. And what I do is that I'm going to separate this a little bit. Instead of just f of t, I'm going to do something like this. Have delta sub a of t times f of t plus f of 0 minus f of 0. So f of 0 minus f of 0, so technically that is 0, so these two cancel out, so that's why I can do that. But now by doing this, I can separate this into two different integrals, so bear with me here. So this one is from negative infinity to positive infinity of delta sub a of t of a functions, that is f of t minus f of 0 dt, plus another integral, but with delta sub a of t times f of 0 dt. So technically this is where, the statement coming from here. You can do that replacement because of this hidden calculations. Remember, we want to take t to 0. The idea is that the impulse is 0 everywhere except at t equal to 0. So you want to let t go to 0. And when you let t go to 0, f of t, take the limit at t equal to 0, so f of t minus f of 0 is going to be equal to 0. So this term is going to be equal to 0. So let me do this. Go to 0 as t approaches 0. Okay. And that's why you're left with just this particular improper integral. Okay. And of course, f of 0 is a constant. You can pull that out of the constant of the integral operations. You have f of 0 times the improper integral from negative infinity to positive infinity of delta sub a of t dt. And this particular integral, again, coming from the idea of the property that the unit impulse function needs to satisfy. Okay. And so this whole thing is equal to to 1, and therefore this is the result you're going to get is f of 0. Okay, and so that's why when you say this particular statement right here, since the impulse is 0 everywhere except at t equal to 0, we can replace the integrand f of t times delta of t by a non-integrand f of 0 times delta of t, because you can do this type of calculations in the limits. That means that you need to take a limit as t equal to 0, and this terms will go away, right? And you left with only this term. Alright, so it's not straightforward, even though the calculation is very simple. It's not straightforward, and it's have to be taken care of. Okay, now this is only the case, a very specific case, when t is equal to 0. When t is equal to t sub 0, that means you translate the concentrations or the delta functions to another place on the right. You shift it to the right by t sub 0 unit. What's going to happen? Is going to be here equal to f of t0. I'm going to show you that very similar to what you see here, right here. That is similarly, we can replace f of t times delta of t minus t0 by f of t sub 0 times delta t minus t0. Then let me explain that a little bit. Since the impulse function is 0 everywhere except at a t equal to t0, then you have that the improper integral from negative infinity to positive infinity of f of t times delta of t minus t0 dt is equal to definite integral from negative infinity to positive infinity of f of t0 times delta t minus t0 dt. And f of t0 is a constant, so you can pull that out of the integral operations, and you get f of t0 times the improper integral from negative infinity to positive infinity of delta t minus t0 dt. And here, right here, this distribution is equal to 1. And therefore, you're only left with the result of f of t0. Okay. So that is the shifting property. And again, it's going to pop up again in convolutions in the next lecture.